Hi again, everyone. We're going to pick up with the rest of Chapter 6 by covering the equations of rational expressions. And we're going to do kind of the same sorts of things we were doing with the last video with all the rational expressions, except now we're going to put them in equations and see if we can't solve them using some of the techniques that we talked about before back in, say, Chapter 1. So if you remember back in Chapter 1, we talked about how first thing we had to do was get rid of all the fractions before we isolated the x. That's what we have to do here, get rid of all the fractions first. And so what I'm going to do is notice in this first one where we have x plus 7 over x equals negative 8, the first thing I would like to do is get rid of the x on the bottom. So what I'll do is I'll take the x that's on the bottom and multiply everything in the problem times x. This will get rid of that x on the bottom, kind of like at the very end. If you remember in the last video, we were talking about how you can get rid of the complex fractions where you have the little baby fractions inside the other fractions. You multiply by the common denominator. This is what we're doing here. And so what happens is these x's cancel. And you're left with x squared plus 7 equals negative 8x. Now, if you have an x squared in the problem, that's what we have here. If you have an x squared in the problem, your goal should be to set it equal to 0 and hopefully factor it. If you don't have an x squared, if you only have an x to the first power, then you do what we did back in Chapter 1, where you move all the x's to one side, all the numbers to the other to isolate the x. Here, since we have an x squared in the problem, I'm going to add the 8x to both sides, so that we can set it equal to 0. And this should factor. Since there's a positive on the 7, that means your signs are the same. And since there's a positive on the 8, that means they're both plus signs. And then you want two numbers that multiply to 7 that add to 8, which would be 7 and 1. So I set each one of those equal to 0. Either x plus 7 equals 0, so I'm up on the top left now, because I'm kind of running out of room on the other part, and x plus 1 equals 0. And we'll subtract the 7 from both sides. Oh, oops. I put 7 on all of them. You subtract 1 on the one on the right. Subtract 1 from both sides. And so what we'll be left with is either x equals negative 7 or x equals negative 1. Now, some of the problems along the way, I kind of mentioned how many solutions you should end up with. There is no good way to look at a rational equation and come up with it's going to have this many solutions because different things will happen throughout the problem. And so sometimes you'll get 2 solutions, sometimes you might get 3 solutions, sometimes you might get no solution. In this case, we get 2. You do have to check to make sure that the denominator does not become 0 by using these numbers, and it wouldn't. 7 divided by 7 would be 1, and 7 divided by 1 would be 7. You're not going to make that have a 0 on the bottom, so those numbers will both be okay. But sometimes you might have to throw some answers out. On this second one, you'll notice there are 2 fractions set equal to each other. The easiest thing to do there is probably something you might remember from all the way back in, say, maybe 4th grade or so. If you have 2 fractions that are equal to each other, you can actually cross multiply them. And so that's what I will do. I will multiply one direction and say x plus 3 times x plus 4. And then that'll be equal to, if I multiply the other direction, x minus 4 times x plus 1. Then what I need to do here is FOIL both sides. So if I FOIL the left-hand side, I'll get the first one's x times x is x squared. The outside, 4 times x is 4x. The inside would be 3x. And the last one's 3 times 4 gives me 12. On the right-hand side, same thing. X times x is x squared. The outside, x times 1 is x. The inside, negative 4 times x is negative 4x. And the last one's negative 4 times 1 is negative 4. If I add those together, I'll get x squared plus 7x plus 12. It looks like I put a negative there, but I didn't mean to. And x squared minus 3x minus 4. Now, here again, I have x squareds in the problem. So kind of my goal would be to get all of the stuff to one side and set it equal to 0. If I attempt to do that, if I subtract x squared from one side to get it to the other, what happens though is that the x squareds actually cancel from both sides. And I'm left with just 7x plus 12 equals negative 3x minus 4. So I'm going to move up here now. Since the x squareds all went away, then it doesn't become a problem where I want to set it equal to 0. This has just now got x's to the first power. So what I want to do is try to isolate that x just like we did back in chapter 1. You might remember I would add 3x to both sides. And get 10x plus 12 equals negative 4. I would subtract the 12 to the other side and get 10x equals 12 and 4 make 16. And divide by 10 on both sides to get the x by itself. And so I end up with x equals 16 divided by 10 doesn't simplify completely, but you can divide 2 into each one and get negative 8 over 5. And in this case, we only got one number for a solution, as opposed to the last one where we got two numbers. And that's what I was saying earlier. There's no real good way to look at a problem and say you're going to get so many solutions. Now, most of the ones that you'll see as we work through some of the homeworks and quizzes and things will look like this, where you have two fractions added together is equal to another fraction. My suggestion here is to simplify or factor the denominators as much as possible. So I would rewrite this as 1 over y minus 2. That one doesn't factor. 1 over 10, which also does not factor. But the third one, there's a 5 in common. If you pull the 5 out, you'll have y minus 2. So I need to multiply by a common denominator, at least common denominator. I need a number that both 5 and 10 go into, which would be 10. And I need the highest power on my terms that I have. So I have 1y minus 2. So I'll need 1y minus 2. So that common denominator will get multiplied by everything in the problem. So I'm going to take 1 over y minus 2. And I'm going to multiply that times 10 and a y minus 2. I'll take the 1 over 10 and multiply that times the 10 and the y minus 2. And on the other side, the negative 4 over 5 times y minus 2, I'm going to multiply that times 10 times y minus 2. And the idea here again is to get all the fractions to cancel off. And so on the first one, the y minus 2's cancel. That's good. On the second one, the 10's cancel. That's good. On the third one, the y minus 2 cancels, and 5 goes into 10 2 times. So what I'm left with is 1 times 10, which is 10. I'm left with 1 times y minus 2, which is y minus 2. And on the other side, I'm left with 4 times 2, which is 8, but it's got a negative in front of it, so it's negative 8. And it simplifies so much. On the left-hand side, the 10 and the minus 2 become plus 8. And then all I have to do is subtract 8 from both sides. And so even though it kind of looked complicated, it just becomes the answer negative 16. Again, you do have to make sure that answer is okay, and it is, because that will not make your original denominators 0. The only number you could not use would be 2, because 2 minus 2 would be 0. So let's do another one kind of like that one. We have 9 over x minus 1 and a 10 over x plus 1 equals 1 over x squared minus 1. I do want to factor the bottom. The x minus 1 doesn't factor, and neither does the x plus 1. But the 1 over x squared minus 1, that's the difference of squares. That is x plus 1. Ooh, that does not look like x plus 1, does it? Try that again. X plus 1 and x minus 1, because the x squared minus 1 is the difference of squares of x squared and 1 squared. So then we come over and say, what's our least common denominator that we're going to need? Well, we're going to need an x minus 1, because I have an x minus 1 on 2 different fractions, both to the first power. And I have an x plus 1 because I have an x plus 1 on 2 different fractions, again, to the first power. So I'm going to rewrite this. And some people don't really need this step where I multiply the x minus 1 and the x plus 1 on each one of them. If you don't, that's perfectly okay. I do suggest doing it just because it helps keep it straighter as you work your way through the problem. You may also hear it thundering outside. It is raining like crazy. Big storm coming through. So once I multiply it on every one of them, some of the fractions, all the fractions should cancel. The x minus 1 cancels the x minus 1. The x plus 1 cancels the x plus 1. And on the last one, they both cancel completely, which is kind of nice. So all you're left with is this 9 that gets multiplied by the x and the 1. And notice this is a negative 10 that will get multiplied across on the x minus 1. So I'm left with 9x plus 9 minus 10x plus 10. Negative 10 times negative 1 is positive 10. And on the right-hand side, all you're left with is the number 1. So negative 9 and the minus 10 on the x's give you negative x, negative 1x, and 9 and 10 give you 19. I would subtract the 19 from both sides. That doesn't look very good. Subtract the 19 from both sides. And I'm left with negative x equals negative 18. And then divide by negative 1 on both sides. And so I'll get that x equals 18. Again, that's an okay answer because the only thing that would make the denominators equal 0 would be either 1 or negative 1. And we didn't get that answer. So 18 is good. By the way, if you want to, you can plug these numbers back in. I do suggest if you do that in the calculator. Type the left-hand side in, 9 over 18 minus 1, which is 17, minus 10 over 18 plus 1, which is 19, should be equal to something. And then you type in 1 over 18 squared minus 1, and you should get the same answer. Okay, let's do another one, very similar. I want to factor it. The bottom right-hand side is the difference of squares, just like the last one was. The only real main difference on this one is that we have an x on top instead of a number on top. The last one had 2 numbers on top. This one has an x on the top of the left-hand fraction. And this will become x plus 3 and x minus 3. Again, the difference of squares. The least common denominator is much like the last one. I'll need 1x minus 3 because there's an x minus 3 on 2 different fractions. And there's an x plus 3 on 2 different fractions. So I'm going to multiply everything times x plus 3 and x minus 3. So I'll have x over x minus 3 times x minus 3 at x plus 3. There's that thunder again. And then 3 over x plus 3 times x minus 3 and x plus 3. And that will be equal to 18 over x plus 3 and x minus 3 times x plus 3 and x minus 3. Had to kind of go sideways. That's about a room. And again, the fractions cancel. The x minus 3 on the first one cancels the x minus 3. The x plus 3 cancels on the x plus 3. And on the last one, everything cancels, which is kind of nice. Here we'll have an x that gets multiplied by the x and the 3. And then a 3 times the x and the minus 3. So I'll end up with x squared plus 3x. Then I'll end up with a 3x and a minus 9 equals 18. So here, this is what I was mentioning a little bit earlier. If you have an x squared in the problem, you got to get everything to one side and set it equal to 0. So that's what we'll do. I will simplify the left-hand side. The 3x and the 3x will become 6x minus 9, not plus 9, equals 18. Then to get it equal to 0, I will subtract 18 from both sides. And so I'm left with x squared plus 6x minus 27. I need, because of this negative sign right here, I need 2 sets of parentheses, with one being a positive and one being a negative. The x squared becomes x and x. And I need 2 numbers that multiply to 27 that add or subtract to give me 6. In this case, subtract. I would do 9 and 3. 9 is the bigger number. 6 is positive, so the bigger number gets the positive. And so at this point, you set each one of them equal to 0. So either x plus 9 equals 0 or x minus 3 equals 0. And we solve them individually. Subtract the 9 from both sides, so you get x. We get x is negative 9. On the other one, you would add 3 to both sides. And so x is 3. Now, if you put both of those answers down, you would be wrong. X equals negative 9 is the answer. It is the only answer. Because this x equals 3 cannot be used. Why can it not be used? We'll go back up here to the top. This little part right here. There's an x minus 3 on the bottom. If I plug 3 into this x right here, I would get 3 minus 3, which is 0. I can't have 0 on the bottom, which means that this x equals 3 that I got down here cannot work. So this one just goes away. And so the only answer you have is negative 9. Negative 9 will not make the fractions be 0 on the bottom. So that one's a little bit tricky. You got to make sure you check those numbers to make sure you can use them or not. Okay, let's try another one. So you might get one solution, you might get 2 solutions, you may not even get a solution. So let's see what happens here. Again, very much like the last one, we have an x on top. So we'll have the x over the x minus 5. That will not change. The 1 over the x plus 5. And the right-hand side will become 50 over x minus 5 and x plus 5. So our common denominator on here is just like the last 2 that we did. You'll have an x minus 5, because that's on 2 fractions, and you'll have an x plus 5, because that is also on 2 different fractions, both to the first power. So I'll have x over x minus 5, which will get multiplied times x minus 5 and x plus 5. plus 1 over x plus 5 times x minus 5 and x plus 5. And that will be equal to 50 over x minus 5 and x plus 5 times x minus 5 and x plus 5. The fractions will cancel again. The x minus 5's on the first one, the x plus 5's on the second one, and again both of them on the third one. So when we multiply this out, we'll have an x that gets multiplied on the x and the 5, and the 1 that will get multiplied on the x and the minus 5. So we're left with x squared, 5x, and x, and a minus 5. On the right-hand side, you just get 50. So we'll simplify the left-hand side by putting the 5x and the x together to get 6x. And because we have an x squared in the problem, I got to set it equal to 0. So to set it equal to 0, I will subtract the 50 from both sides and get x squared, 6x, and a minus 55. And just like the last one, we have a minus sign next to the 55, which makes a positive and a negative in my two blanks for my factoring. I need two numbers that multiply to 55, which the only two numbers that multiply to 55 are 11 and 5. So you're going to have to use 11 and 5. And then that give you a positive 6 in the middle. So the 11 would have to go on the positive, and the 5 would go on the negative. Set each one equal to 0. Either x plus 11 is 0 or x minus 5 is 0. And solve each one. If I subtract the 11 from both sides, I'll end up with x equals negative 11. If I add the 5 to both sides, I'll end up with x equals 5. And again, you have to check. X equals negative 11 is a perfectly okay answer, but x equals 5 is not, for the same reason it was on the last one. If you go back up to the very top on the left, there's an x minus 5 right there. That x minus 5 right here, if I was to plug that 5 in, I would end up with 5 minus 5 on the bottom. So that means this answer down here that I got, this x equals 5, cannot work. And so I have to toss this one out and say my answer is only negative 11. Okay, let's try this one here. This one can be factored on the bottom as well. We'll end up with a 1 over an x plus 3, a 7 over an x plus 5, and the way you factor the one on the right is, since it's a positive on the 15 and a positive on the 8, we'll put positives in the blanks. The x squared will become x and x like it always does. And two numbers to multiply to 15 would be 3 and 5, because 3 and 5 give me 8 if I add them. So much like the other ones, my common denominator will just be the stuff that's on the bottom. The x plus 3, that's on two fractions, and the x plus 5 is also on two different fractions. So I'm going to multiply everything by x plus 3 and x plus 5. So I'll do 1 over x plus 3 times x plus 3 and x plus 5. I will do 7 over x plus 5 times x plus 3 and x plus 5, and set that equal to 2 over x plus 3 and x plus 5 times x plus 3 and x plus 5. So like on the rest of them, the x plus 3 on the first fraction cancels, the x plus 5 on the second fraction cancels, and the 2 on the bottom of the third fraction cancel completely. So I'm left with 1 times x plus 5 and 7 times x plus 3. So I'm left with x plus 5 and 7x, and 7 times 3 is 21. Set that equal to 2. There is no x squared here, so we're just going to try to isolate the x's. So 7 and 1 give me 8x, and 5 and 21 give me 26, equals 2. Subtract the 26 from both sides. So I'll get that 8x is negative 24. And we'll divide by 8 on both sides. And so it looks like x equals negative 3. Again, you have to check it. Now, we only got one number here to check. And if I checked it, you have a problem right here at the top on the left. Just like on the last two, if you were to put negative 3 right there where that x is, negative 3 plus 3 would be 0. And I cannot make 0 on the bottom. Which means this number, the only number that I got, cannot be used. So this problem has no real solution. There is no number for x that will make that work. So, like I said, you could have no solution, you could have one solution, you could have two solutions. You don't know without actually working the whole thing out. Okay, now we're going to jump into doing some word problems along with this. So we have about 5 or so word problems that I'm going to be working with here. First of all, we have a private plane that's traveling from Seattle to somewhere out in the rugged wilderness, and that plane is traveling at an average speed of 330 miles an hour. Going backwards back to Seattle, it's going 275. It must have a headwind going the other way because it's not going quite as fast. The total traveling time was 5 hours. So how far is Seattle from the wilderness? This is a distance, rate, time problem. And you'll notice that in some of the problems, you'll see something that looks like this, where it says there's a total amount of time. That tells you a formula that you'll want to use. That formula looks like this. The distance divided by the rate plus the distance divided by the rate equals the time. Distance over rate plus distance over rate equals time. So what we will have is two different rates, and we have a total time. The distance from Seattle to the wilderness is the same whether you're going one direction or the other. And so we will solve this as d, and d being the total distance, being the distance between the two places. The rates will be, one of them is 330, one is 275. So you'll put 330 on the bottom of one, 275 on the bottom of the other one, and it's equal to the total time, which in our case was 5 hours. So we set it equal to 5. And you solve it for d. We could have actually done this type problem back in chapter 1 or 2. There's no d's, no unknowns on the bottom, so we could have done it back then. But I'm going to multiply everything in the problem by a common denominator. Now, what's the least common denominator between 330 and 275? I ain't got a clue, and I'm not going to worry about it. What I'm going to do is multiply everything in the problem by just those two numbers multiplied together. So we're going to multiply it times 330 and 275. And then we'll do d over 275 times 330 and 275, and set that equal to 5 times 330 times 275. That way, if I do it like this, I automatically know that the 330s cancel and the 275 cancel. So I'll end up with 275 times d plus 330 times d equals, and then I'm going to have to go to the calculator and figure out what 5 times 330 times 275 is. So if you didn't know, it's 453,750. So that's a 50. It doesn't look like a 50, but that's supposed to be a 5 right there. The 275 and the 330 added together give me 605. So I have 605 times d equals 453,750. And then just divide by 605 on both sides. And I'll figure out that the distance was, pause for a moment while I go back to the calculator, 453,750 divided by 605 equals 750 miles. It is 750 miles from Seattle out to wherever that wilderness is. But the key thing is, if you read through a problem, if it ever says that there's a total time of a certain amount, this is the formula you want to use. This is your total time formula. Okay, another formula that you'll probably want to look at is called a same time formula. Sally can paint a room in 3 hours. It takes Steve 6 hours. How long did it take them to work together? Oh, sorry, this is not a same time problem. I thought it would be. This is actually a work problem. So if you're going to do a work problem, so or a job problem, sometimes it's called a job problem, where you have two people or two things working together to reduce the amount of time it takes to do something. Like Sally and Steve are going to work together, it should take them less time to do the same process, the same painting the room, if they work together. So this has a different formula. This is time alone. Oops, sorry. I wrote it backwards. Time together over time alone plus time together over time alone equals 1. This is your formula you want to use on these type problems. So our time together is what we don't know. How long would it take them to paint the room if they worked together? That's what I don't know. So I'm going to let that be x. So I'm going to have x's on top. The time alone, Sally can do it in 3 hours. Steve can do it in 6 hours. So I put those on the bottom. Then, again, kind of like the last one, notice there's a common denominator, the 3 and the 6. A number that both 3 and 6 go into would be 6. So what I could do is just multiply everything in the problem times 6. The 6's would cancel on the first one, and 3 goes into 6 2 times. So I'm left with 2x plus x equals 6. Or 3x equals 6. So if I divide by 3 on both sides, I'll end up that x equals 2 hours. So Sally can do it in 3 hours, Steve can do it in 6 hours, but if they work together, they can do it in 2 hours. So they're shaving off a little bit of time. Sally just a little bit, but Steve a lot. Okay, this is another work or job type problem. We have Ken and Betty who want to clear their driveway. Ken can do it in 3 hours. Betty can do it in 6 hours, but a little bit of a difference here. Betty works for 2 hours before Ken joins her. So how much longer will it take for them to do this job together of clearing their driveway? So just like on the last one, it's the time together over time alone plus the time together over the time alone equals 1. So that's my formula I'm going to use. The time together is what I'm kind of looking for. I know the time alone. Ken can do it in Ken can do it in 3 hours. And Betty can do it in 6 hours. So, to give you a little bit of clarity here, the first one is your Ken fraction, and the second one is your Betty fraction. So one of them needs to be X, but one of them needs to take into account that Betty works for 2 hours before Ken joins her. So if Betty works 2 hours already, then if we let Ken be X, Betty would be X plus 2. She worked 2 more hours than he did. If you let X be if you let X be Betty, then Ken would be X minus 2. So it just kind of depends on how you write the problem. And so we'll solve it, kind of like the rest of them. The 6 and the 3 on the bottom have a common denominator of 6. So I'm going to multiply everything in the problem times 6. That way, on the middle fraction, the 6 is canceled, but on the first one, 3 goes into 6 2 times. So I'm left with a 2x and an x plus 2 equals 6. Or that's 3x plus 2 equals 6. Then I could subtract the 2 from both sides to get that 3x equals 4. And this will not divide evenly like some of the other ones have done so far. So I'll get that x equals 4/3 of an hour. That's an hour and 20 minutes if you want to think of it in terms of hours and minutes. It's a whole hour and then a third of another hour. So about an hour 20. Now you have to remember, what are you looking at for the answer here? How much longer will it take them would be the x value if we set it up with x being Ken. Because Ken will be the one that works together with her for this amount of time. If you did x minus 2 on Ken and you did x on Betty, you would have found a different number. You would have found the total amount of time it took Betty to do it. And then you'd have to subtract 2 from it to see how much longer it would take them. So that's why I put the x on Ken, to see how much longer it will take when they're actually working together. Hopefully that makes sense. Okay, like I mentioned earlier, there's a total time problem, and then there's another type of problem that's called same time. So somewhere in the problem you might see it says that something happens in the same amount of time as something else. So if you ever see a same time problem, what you do is your distance divided by your rate equals your distance divided by a rate. Like in this case, Jennifer walks 5 miles. That's a distance, so it goes on top. In the same time, she can jog. Oops, bad spelling. She can jog, not job. She can jog 10 miles, so that's a distance, so that goes on top. Her jogging speed is 8 miles an hour faster than her walking speed. Remember back when we did word problems before, I said we could let the thing at the end of the phrase be x. That's what we're going to do here. We're going to say her walking speed is x. And so since she walks 5 miles, I'm going to put the x underneath the 5. And it's 8 miles an hour faster, tells me I have to do x plus 8 on the bottom of the other fraction. If it was 8 miles an hour slower, I would do x minus 8. And all we have to do here is cross multiply. Do the 5 times the x plus 8 and the 10 times the x. Cross multiplying this direction and in that direction. So I'll get 5x plus 40 equals 10x. I can get the x's all to one side by subtracting the 5x over. And then divide by 5 on both sides to get the x by itself. And 40 divided by 5 is 8. Now, some of these problems are not realistic. we found how fast she walks. That's the x value. That's her walking speed. Most normal human beings do not walk at 8 miles an hour. Most walk somewhere between 2 or 3 miles an hour. That means she jogs at 16 miles an hour. So if she was to sprint, she could probably get up to about 25 to 30. Again, not very realistic, but that's the process that you go through. Okay, if Joe rides a bike to his office, he averages 6 miles per hour. If he drives his car, he only averages 12 miles per hour. His time traveling is half an hour less than his time bicycling. How far away do you think his office is? And so this one's a little different than the rest of them. Notice it doesn't really say total time in the problem or same time in the problem, but it's still a distance rate time problem. Your distance is always equal to your rate times your time. And so what we have here is he rides a bike to his office, he goes 6 miles per hour. He drives a car, he goes 12 miles an hour. But the thing to remember is the distance from his starting point to his office is going to be the same whether he drives or he bikes. Makes sense, right? And so, if I have one distance would be the rate, 6 miles an hour, times the time. I don't know what the time is. But the other one is the same distance would be 12 miles an hour, but it's t minus a half. Because that half comes from he was half an hour less if he drives. So you have to take off the 1/2. Since the distance is the same, we set these two equations, these two, can be set equal because the distance is the same. So I could say that 6t equals 12 times t minus a half. Notice I'm not actually solving for the distance here. I'm actually solving for a time first. And so if you multiply the 12 across, 12 times t is 12t. 12 times a half would be 6. If I subtract the 12t off to get all the t's to the same side, I'll get negative 6t equals negative 6. And then I could divide by negative 6 on both sides to get that t equals 1. And in fact, that would be 1 hour. That is not your answer, though, because your answer needs to say how far away is his office. You can't say his office is 1 hour away. You know, we do that a lot in Mississippi for some reason, but that's not technically legal. So what you have to do is then take this value you just got and plug it back in to either one of these equations. I'm just going to do the top one and say that my distance is 6 times my 1 hour. So my distance is 1 times 6 is just 6 miles. So he can bike that 6 miles and he's getting 6 miles per hour average. Or he can drive it, so it must be pretty bad traffic to take that much time, and he only averaging 12 miles per hour to go those 6 miles. But that's how you would do that problem. Okay, one last problem, and then we'll be done with all the word problems from here on out, which is kind of nice. Here, this is a work type problem again, where you do the time together over the time alone, and the time together over the time alone equals 1. So what we have is a swimming pool that can be filled in 11 hours if you go through a pipe, or 20 hours if you go through a hose. If water's entering through both of them, how long will it take to fill the pool? So again, two things here are working together to accomplish one job. That makes this formula over here. So the time together is what I'm looking for. I'm looking to figure out how much time it would take to fill the pool. It's always equal to 1 on a job or a work problem as well. One of them can fill it in 11 hours. The other one can take 20 hours. So what I would probably do here is just multiply everything times 11 and 20. That would be kind of the easier thing to do as far as common denominators and such on this problem. So I'll multiply by 11 and 20, including the 1 on the right-hand side. The 11s would cancel. The 20s would cancel. So I'm left with 20x and 11x equals whatever 11 times 20 is. 220. Oh yeah, I should have known that. So I'll get 31x if I add the x's together on the left-hand side, 20 and 11, and then divide by 31 on both sides. That probably will not go in evenly. Not even close, I bet. So 220 divided by 31. Oh yeah, that's not even close to being a nicely done thing. So you can either leave it as 220 over 11 hours, or they might ask you to approximate, because most of the time you're not going to get a value of, someone asks you how much time does it take. You don't usually say 22 divided by 11 hours. So if you put it as a decimal, just to make sure you're getting the same kind of value that you should get, it's about 7.1 hours. So one of those two type answers would work. So together, you're cutting off actually a little, 4 hours almost off your best time doing it through the pipe by itself. So that is the word problems and the equations. The main takeaway from all of it is you've got to get rid of the fractions first, and do that by multiplying by the common denominator. And if you do that, then it turns into either something from chapter 1 or from the previous chapter in chapter 5 if it has an x squared in it. The last chapter that we'll do is all about radicals, so that'll be the next video.